Okay. All right. As you may guess, today is a rather important day if you read the title of the notes, because the theorem that we're going to look at today is called the fundamental theorem of algebra. So it is something that, as far as algebra itself goes, algebra being the way that we manipulate symbols, you've been doing algebra for a while. We don't really call it algebra in our classes anymore. Like 10 years ago, we taught Algebra 1, Geometry, and Algebra 2. Math 1 is essentially Algebra 1. It's pretty much the same stuff. All of your solving equations stuff is algebra. That's what you've been doing. And today is the fundamental theorem of algebra. So it has great importance for the whole field of algebra. Now, I will tell you that what we have to learn about it is fairly simple to apply. It's not really incredibly complex. So I think you can do pretty well with this. Although it is the fundamental theorem of algebra, it's not like the hardest thing there is to do in algebra. It's just essential to a lot of the understanding of algebra. So we're going to work on a little bit of vocabulary first. So a polynomial is an expression of more than two algebraic expressions. Let's see. Oh, no, never mind. That's not expressions, and my stupid eraser does not work. That should say terms. Expressions could possibly be used there, but terms is really what I meant to put, because otherwise the second one does not make sense. All right. Jasper, go ahead and close your computer. We won't need it for this. All right. Terms are going to be separated by plus or minus signs. Okay? So an example of a polynomial would be something like this. X to the third minus 5x squared plus 4. That's an example of a polynomial, right? In this case, you would have x to the third would be one term, negative 5x squared would be one term, 4 would be one term. All right, so that would be a polynomial with 3 terms, and we're going to look at naming these things here in a second. So anytime you see a plus or a minus sign, it is separating out a term. Right? One thing that we're going to talk about a lot, and it's really essential to the fundamental theorem of algebra, is the degree of the polynomial. The degree of the polynomial is the greatest exponent of a variable in an algebraic expression. So if I did another polynomial, if I had 7x squared minus 5x to the fourth plus 2, what would the degree of that be?
7x.
Nope.
5x.
Okay. The degree is actually only the exponent, right? So it would come from 5x to the fourth, but it would just be the 4. That would be a fourth degree for that. So it's just the exponent. You wouldn't use the whole term, just the exponent for it. Okay? So whenever we talk about polynomials, there are certain names that we give them based on their degree and their number of terms. So this has a list of the different names that we use. So we name polynomials based on their degree and their number of terms. So if we have a degree of 0, then that is a constant. 1 is linear, 2 is quadratic, 3 is cubic, 4 is quartic. If you have 5 or more, it does not have a special name anymore. We just say it's a polynomial of blank degree. So if it has 5, we'd say 5th degree. If we had 15, we'd say 15th degree, right? So anything above 5 does not have a special name. We also can name these by their number of terms. Now, technically, this first one is not a polynomial. Because the prefix poly, what does the prefix poly mean? Multiple, more than one, right? What does the prefix mono mean? One. So if you only have one term, technically it's not a polynomial, but I need to include it in the list here somehow. So 1 is called a monomial. Technically it's not a polynomial because there's only one of them. 2 is a binomial. Bi is a prefix you're probably pretty familiar with. It always means 2. Trinomial, like a tricycle, is going to have 3. And anything 4 or more, we just say it's polynomial with that many terms because there's not special names for those. Okay, so this is a slide that you might want to keep in mind. For this, being able to name these can be important. I'm sorry about that. Except for that is the elementary school. Let me. If that's the case. I was afraid Henry was sick. All right. Okay. Back to work. All right. Let's look at this. We are going to name these by their degree and their number of terms. I'm going to do the first couple together, then I'm going to let you try the others. So if I look at the first one, I'm looking first for its degree, which is its highest exponent. What's the highest exponent there? It is the cube. It is 3 right there. So that is going to be cubic. Typically, you're going to say the degree first and then the type of polynomial it is normally there. And then I need to look for the number of terms. So right here is a term. I don't know why it's not letting me change colors. This is all messed up. Yeah, I think I just need to try like uninstall that and install it again. It's not working like it's supposed to. All right, so I've got 1, 2, 3, and 3 terms is a trinomial. Right? Does that make sense? All right, you guys just try the others. There, name all of those for me. Four instead of 2, so I don't really know where that name comes from, and I need to look that up. All right, the last one is a little bit tricky. Angel, what have you got for the last one? Nothing. All right, what do you think? How many terms? 2, so that makes it what? Binomial. What's its degree? It is linear. Good. Okay, it is linear because you have a degree of 1, but I don't see an exponent of 1 anywhere. Where is it? The x has an invisible 1 with it. If something does not have an exponent, it has an invisible 1. Okay? All right, now, these are just fancy words, but they can be important because you could have a question that might talk about which binomial is the correct answer, and you need to kind of know what you're looking for there. Yes?
What happens if there's 2 of the same numbers, like 7x, 4, and then another 7x?
What you would do with those is like combine them, and it would become like 14x to the fourth. So it would still have that same degree. Whatever, even if it's there more than once, whatever is your highest exponent is still your degree. That's a good question. Now, I don't think you're going to see that like you would usually combine them, so it would change like how many terms you have if you combine them there. I'm going to give you probably like one of these or something on a quiz or a test, just to make sure you know it, because it's really good for us to know the formal language of math, right? Is it of utmost importance? I don't think it's the most important thing that we learn in here. But if you get, any of you ever went and watched like Khan Academy videos and you're like, I have no idea what this guy's talking about. He like uses a lot of big words. I think he uses really formal language. It's good as a mathematician. Like, it's important to be very precise, but sometimes it's a little much for kids to follow. So if you know this stuff well, it helps you understand whenever you're hearing somebody talk about it. If you find yourself in a college math class, it is probably going to be taught by somebody who, or a decent chance, they definitely are going to have like a master's degree in math. They might have a PhD in math. They will not talk even the way I talk, much less the way you guys might talk about math, where you say, instead of saying exponent, you say that little tiny number, or instead of saying the coefficient, you call it the big number. Things like that. It's not bad necessarily to do that, but it's better to use that formal language for that. So, plus you sound fancy when you do it. So, a little bit more vocabulary. For everything we have seen so far, we have talked about zeros. And the zeros we have talked about so far have been the x-intercepts of a function. Also, sometimes called the, I think I mean roots right there, but let me see if I did this on this. Hold on. Let me see. Look at this trick right, oh yeah, look at that trick right there. I do this to help myself remember. Alright. Also called roots. Okay. Another very similar term that you're going to see is called solutions. Okay. Solutions are the values that make an equation true. Now, our vocabulary is going to change just a little bit for what types of problems we are going to see here, okay? Because we have to start considering some different types of solutions that you could possibly have. All right, so the fundamental theorem of algebra states that every polynomial function of positive degree n has exactly n complex zeros. So if something is of fourth degree, it should have 4 complex zeros. Now, let's just look at Desmos a little bit for this to think about what's happening here. So, if I were to graph f of x equals 3x to the fourth minus 2x squared plus 6x minus 10. I'm going to make this one 16. No, that makes it worse. Let's do minus, not having any luck making this look like I want to. Let's do, okay. Okay, So here is an example of like what we would think it looks like. This, would you guys agree that is a fourth degree function? That highest exponent right there is 4. So what the fundamental theorem of algebra tells us is if we have 4 fourth degree, then we have 4 zeros. Now, they use that word complex. You guys probably don't like to see that word show up in math, right? Now, this function right here, the zeros are your x-intercepts if they're real zeros. So 1, 2, 3, 4, right there it shows up, right? But if I change this, if I put an x right here and put a minus 10, okay, would you guys agree? Still a fourth degree polynomial. Why not? Well, here's the problem. The degree only matters about your highest exponent. Is my highest exponent still 4? It is. How many zeros do we have, though? Just 2, right? I've just got 2 places where I cross the x-axis. So this is why they threw that word complex in there, okay? So we got to make a new definition of zeros for this fundamental theorem of algebra to be true. Teachers have not thrown stuff at you very much that did not have real zeros yet. Maybe in Math 2, I'm not sure if you look at it there or not, but I know you don't spend much time with it if you do. So, instead of calling a zero an x-intercept, zeros are values that cause the function to have an output of 0. Okay? Alright, now, if it's a real zero, it's just like the 0.40, and that's an x-intercept, or 70, it's an x-intercept. But, have you guys ever learned about, let's see, let me make sure I don't have a slide on this first. No, I don't have a slide on that. Okay. Have you guys ever learned about this? I'm not sure. I think you do it in Math 2, but it's been so long since I taught 2, I can't remember. Have you guys ever learned about the square root of negative 1? Okay? Like, what is the square root of positive 1? It's just 1. Because the square root says what number times itself equals that number, right? So, like, square root of 1, 1 times 1 equals 1. So, square root of 1 is 1. Square root of 4, what is it? 2. All right? What is the square root of negative 1? All right, 0.5 times 0.5 equals negative 1? That equals like 0.25. What number times itself gives you negative 1? 1 times 1 is 1. Negative 1 times negative 1 is positive 1. Is there any number times itself that would give you the square root of negative 1? There is not. But the problem is this shows up in math a lot. Like, we try to solve problems, and we got a negative underneath the square root. And we're not going to go into great detail with this now. I just need you to know where this comes from. So, mathematicians decided at one point we need a way of dealing with this because it keeps showing up, and it keeps showing up, and it keeps showing up. But we can't, like, calculate it because it doesn't, like, really exist, right? No real number times itself equals 1, or negative 1. So they decided to give this value right here the letter I. There. I've got a joke back there on my board, and it looks like this. You got this guy. He's jumping up, I guess. And you got this guy right here. And he's wearing glasses. And this guy is calling him square root of negative 16. What is he calling him? Mm-mm. Mm-mm. 4 i's. Because what's the square root of 16? 4. And then it's got that negative, which is -1, and you put an I with it. So it's it says it's back there on my board. It says mathematical insults. I love math jokes. They're my favorite. If you find a good math joke, send it to me so I can print it out and add it to my board back there. So anyway, I went through all of that to tell you that there are numbers that we cannot really work with very well because they've got negatives underneath the square root. And to deal with those, we have to use this I right here. And I'm going to tell you the name of it. Sometimes I don't even tell you guys the name of it because it just makes kids mad. The I, if something involves an I, it's called an imaginary number. And it just makes kids mad because then they want to fuss about having to deal with numbers that are imaginary. I will tell you that they are essential for dealing with a lot of things that happen in some high-level math that make things like your cell phone up there work, right? So it's important at a level. You're probably not going to need imaginary numbers in your daily life ever. But any value that includes an imaginary value, we call that we can call it an imaginary zero. And that's what's happening over here in this graph. We have 2 zeros that are what we call real zeros. They're x-intercepts. We can see them cross the x-axis. They are real zeros. But we have 2 more that are imaginary zeros in this case, which I know is a little bit of a confusing thing to think about. But when we look at like this in practice, it's really not going to be all that difficult, because we just need to be able to recognize it on a really basic level. All right, so real zeros are x-intercepts of a function, right? We can see them on the graph cross the x-axis, okay? Imaginary zeros are values that cause the function to equal 0, but do not show up on the graph. These values include the imaginary value I, and imaginary zeros always come in, make sure you fill this right here, pairs. Okay, so if you cannot have an odd number of imaginary zeros. Okay, now I should put here, we might want to add this on here, complex zeros are any type of zero. Okay, so you might see a question ask how many complex zeros does this have and what type. Complex can be real or imaginary. It includes everything there. Okay, so whenever we graph something, we can only see the real zeros. And then real zeros might have different multiplicities. That means like how many times they count. Okay? Real zeros with an odd multiplicity will cross the x-axis. Okay? Real zeros with an even multiplicity will touch the x-axis, but not cross it. Sometimes I'll call this a bounce. That is not a professional mathematical term that your PhD math professor is going to recognize as good, but it kind of makes sense when you look at what the graphs look like here in a second. Okay? So, let's look. Okay, questions so far? All right, let's keep going. Okay, the function to the left is a 5th degree polynomial function. Determine the number of real and imaginary zeros for this function. Okay? So, there can be more than one answer to this problem. Okay? if I have a 5th degree polynomial, how many complex zeros am I going to have? I've got to have 5, right? 5th degree, 5 zeros for sure. But, so whatever numbers you put in these blanks have to add up to 5. Okay? If you have 2 and 2 or 2 and 7, then you're wrong because those don't add up to 5. So whatever numbers you have right here have to add up to 5. So let's look at this. When you look at the graph, you can see the real zeros, right? So right here, those 2 points right there are your real zeros. Now, what type of multiplicity do I have right here at 0? Is it going to be even or odd? Odd. All right, so this is odd multiplicity. What about over here at 2? Even multiplicity. Okay, this is what it means. The zeros for this function, the very least number I can have is just x equals 0, just one time for this, right? What's the very least number I can have that would be even? 2, right? So that means x equals 2 would have to be there at least twice, right? So the very least number of real zeros you could have here would be 3, okay? Now, there's more than one answer to this question. So one answer could be that you've got 3 real zeros. Now, you have 3 real zeros, you only have 2 distinct zeros, okay? So when you say you have a multiplicity of 2, it means that number like shows up 2 times, right? So distinct means they're separate, but real could be repeated, right? So if I have 3 real zeros, how many imaginary zeros you cannot see on the graph? How many imaginary zeros would I have? I'd have 2, okay? That's an option right there, okay? What is not an option is 2 and 2. 2 and 2 does not add up to 5, so it can't be our answer. Another thing that is not an option, could I do this? Could I have 2 real zeros, 3 imaginary zeros? We cannot because of something we wrote on one of those slides earlier. Let's see where it was. It was back here. I think it was right here. On this slide right here, it says imaginary zeros always come in, what do we put in that blank? Pairs. So, imaginary zeros, this number always has to be an even number, right? Because they always come in pairs. So, it would be impossible for that to be the case. It can't be 2 and 3. Now, there is one other thing that you could have. Anybody know what another option there? Can't have half a 0. So that would not work. Plus, imaginary zeros have to come in pairs, so 2.5 wouldn't be a pair for that. Can't have an odd number for imaginary zeros. I cannot have 1 real 0 because I definitely have 2 x-intercepts right here. So, since I can see them on the graph, I've got to have 2 or more, right? And in this case, really, it has to be at least 3 because I know I have even multiplicity here, right? So, I've got to have at least 3 real zeros. When I see this as odd multiplicity, it could just be there one time. What's another option? What's the next biggest odd number we could have? We could have 1, or we could have, that would not be the next biggest odd number. What odd number comes after 1? 3, right? So, like, that could be there 3 times. We could have a multiplicity of 3. So, it could be, you could have 5 real zeros and 0 imaginary zeros. That's the option for that. The way you're going to see this most of the time is it's going to be multiple choice, and they, of course, will only have one choice that is correct there. All right, let's keep going. I know this seems a little confusing at first, but hopefully it will get more clear as we go. All right, so in this problem, we have a 6th degree polynomial. So what if I add these two together, what does it have to equal? Total has to be 6, right? So number of zeros always equals the degree. It has to equal 6. If I have 1 and 4, I've messed up, right? That does not work. All right, so if I look at my zeros, I've got 1, 2, 3, 4, 5. So could it be 5 and 1? No. Why can't it be 5 and 1? You imaginary zeros. This has to be an even number. Okay? But can it be 4 for the real zeros? How many can I see on the graph? I can see 5. So I can't ever bump that number below what I can see, right? So let's think about multiplicity here. This one, this one, this one, and this one all have odd multiplicity. That means if I was listing them, I would have x equals 1, probably just one time, x equals 2, x equals 3, and x equals 4. But what happens right here at 0? Do we cross the x-axis at 0? We do not. This is even multiplicity. That means that this has to be there at least twice. X equals 0 and x equals 0. It would show up in our list twice, right? Now, how many have we got there if I list them out like that? 6. That's what we need, right? So what's happening here is we've got 6 real zeros. One of them has a multiplicity of 2 because it bounces. And then if I got 6 real zeros, how many imaginary zeros do I have? 0, because it has to add up to 6, right? That's your only option on this particular problem. Okay, let's keep going. All right. So the function f of x equals x to the 5th minus 3x to the 4th minus 32x squared minus 81x minus 45 has zeros at x equals 5 and x equals plus or minus 3i. Tell the number of real and imaginary zeros for f. And this one is where Desmos does come in handy, so I'm going to graph this, but it's not worth getting your computers out for here. You can just look at what I've got up here. So let's graph. First of all, what degree do we have?
5.
Yes, 5. All right. Okay, so how many zeros do we see on this graph? I see 2. There's got to be a total, though, of 5, right? That has to be a total of 5. So could I do 2 here, 3 here? That adds up to 5, but it does not work. Why does it not work? What did I say about those imaginary zeros? Even numbers only. This will not work. It is not 2 and 3. It feels like it should be because I can only see 2 zeros right here. What's special about this 0 right here? It bounces, right? It does not cross the x-axis, which means that it has what type of multiplicity? I heard it back here. Odd. No, not odd. Even, right? Which means it probably counts twice in this particular case, right? So, although this only looks like 1, it counts twice because it bounces. So you got 1, 2, 3 real zeros. Now they told me that one of the that some of the zeros were at plus or minus 3i. What type of zero do we have whenever we have an I with it? The I stands for what kind of number? Square root of -1, which is imaginary, right? So by putting that plus or minus, what they mean is x equals positive 3i and x equals negative 3i. Remember, they always come in pairs. You have to have even numbers. So you've got 2 imaginary zeros. Okay. Let's look at 6. What degree do I have on that polynomial? 4. So what's the total going to be? It's going to be 4, right? So the total has to be 4. If I graph it really quickly, f of x equals x to the 4th minus 8x to the 3rd plus 14x to the 2nd plus 28x minus 80. All right, how many zeros do I see? Okay. Are either one of those like double zeros or have a multiplicity of 2? No, they just cross one. So they could be, I mean, it could be a triple zero. It could be like 5 zeros there at once. But do I have any imaginary zeros? What does it tell us right there? X, one of the zeros is that x equals 2 plus I. So I've got an imaginary zero, at least one. And even though they only told you one of the imaginary zeros, if x plus I is a zero, it has to have a pair, right? So even though they only gave me one, I know there's got to be 2 because it's got to have a pair with it, which means that these 2 zeros that I see here are just my 2 real zeros, right? It's got to add up to 4. Okay, questions so far? Okay, let's talk about end behavior. Okay, end behavior we've already talked about some. It's just what happens on the very far ends of the graph, right? Whether it goes up or down or levels out at a number. The good news for these types of problems is they never level out at a number. They either go up or they go down. So, you've got 4 options here. First of all, polynomials always have a domain of negative infinity to infinity. So when you see this right here, as x approaches negative infinity, this just means left side, right? And our other part, as x approaches positive infinity, that means right side of the graph. Now, if you're looking at a graph, you're just looking to see whether the ends go up or go down, or one of them goes up and the other goes down, or they're switched, right? Those are your 4 options. There's only 4 options for how these can look. So if we look at this graph on the left side, what happens on that left side as x approaches negative infinity? What happens to our y? It approaches positive infinity because it is going up, right? What about on the right side? Also approaches positive infinity. Now, you're able to use Desmos, so if they give you the equation, you can graph it, but there's a trick for this, okay? So, if you have even degrees, so if it's 2nd degree, 4th degree, 6th degree, etc., then the 2 sides are going to go the same direction. They either both go up, both go down. If there's a positive leading coefficient, that is the number. So like, for example, if I've got f of x equals 3x to the 4th minus 6x squared plus 2. My highest term is that x to the 4th, right? 4 is the degree. Then if I look at this number in front of the term, that positive 3, if that number is positive, both will go up. If that number is negative, both will go down. Right? If you have odd degree, then they'll go opposite directions. Okay? So let's look at some problems here. Okay? For this one, so we're just looking at graphs right now. Assume there is an arrow right here. As x approaches negative infinity, that's the left side. Keely, what happens to this graph? What? Right. Does it go up or down on the left side? It goes up on that left side. And up is to positive infinity, right? So as x approaches negative infinity, our y values approach positive infinity. But, Keely, on the right side, what happens to my graph? Down. So that means as x approaches positive infinity, y approaches negative infinity. Right there. Okay, let's think about doing it without a graph. Okay? If I have, first of all, for 8, I have a degree of what? 3. All right, so that degree right there, being 3, that's an odd number. That tells me they go opposite directions. Okay? When we see they go opposite directions, we want to look at the number in front. Okay? And that's, whether or not it's positive or negative is going to tell you what the right side does. Okay? So that number is positive. If that number is positive, that tells you that the right side is going to approach positive infinity. The right side is that second statement usually, right? This is your right side. So this one would have to approach positive infinity. What would the other side have to approach? It'd have to be negative because they're opposite each other. Okay? Let's look at example 9. What degree is that? 4. That's your highest exponent. So 4 tells me that they're going to do the same thing. They either both go up or both go down. Right? It's even, so they both go up or both go down. We want to look at the number in front of that term, which is a negative 2. So that, you can think of it, that's going to tell you what your right side does every time. So that tells me my right side goes to negative infinity because it's a negative number. But since they're the same, it also tells me the left side also goes to negative infinity there as well. Now, you can use Desmos to graph it, but you can answer these really quickly if you do not. Okay? Because in particular, like a place where you'd be worried about having to answer this very quickly would be on the ACT. This is the type of problem that might show up on the ACT. And if you know that trick, you can answer it in 10 seconds versus having to type it in Desmos and it take you a minute to do the problem. And there is not much time on the ACT. Okay? All right, we got, is this the last one? Okay. All right. All right, so these are just slightly different here. It's asking for your possible solutions. What's different about these is these aren't functions, right? These are equations. They have an equal sign in them. So that means instead of calling them zeros, we would call them solutions. But the same thing still holds true. You're going to look at the degree right there. And whatever the highest degree that you see is, that's the number of possible solutions that you have. So this one would be 2. What's the degree for number 11? It's 5. Always look, you gotta look at the whole thing. It doesn't have to be the first term. So that could have up to 5 solutions. Okay. What about number 12? That one's only got 1 solution. What about number 13? 8. solutions. Possible solutions. It may not have that many real solutions for sure. Okay? All right. So,